This is going to be a very abbreviated version of the library of functions, but extended. Abbreviated in that it's a review, but extended in that it has more stuff in it. Usually when we talk about the library of functions, we limit it to polynomials and rational functions, but since you have first learned the library of functions, you should have already learned a bunch of trig and also exponential and logarithmic functions. So we're going to be talking about all four kinds of things: polynomials, rationals, logarithmic and exponential, which is kind of categorized together, and also trig stuff. Alternative names for this would have been the function cookbook or the restricted section in the library at Hogwarts. For polynomials, we have our increasing degrees. So you start with a constant. There's your parent function for a constant. It's a flat line. Then linear. And then after that, you have quadratic with x squared. The next one you have is cubic with x cubed. And the next one is quartic with x to the fourth. Polynomials keep on going on, but we're not going to see a whole lot more than that here. An interesting tidbit about polynomials is that they can only have one fewer bump than whatever the degrees at max. So, a few of these. If I have this, I can move this around. This is my constant. I can move around like that. If I have my linear, okay, its power is 1, which means that the most bumps it can have is 0. So when I move things around, this is linear, these are linear. I can move them both. These are all linear. But you see how it has a degree of 1? Therefore, the max number of bumps it can have is 1 less than that, which would be 0. 0 bumps. Now, quadratic, the power is 2. The degree is 2. And so therefore, the max number of bumps I can have would be 1. So I can turn these on, and these things can move around. So we can only have 1 bump. And here is one that is cubic. Let's move all these back. So it's cubic, so you see how the degree is 3, and therefore the max number of bumps it can have is 2. Here's something that is quartic. It looks like it's a parabola, but when I start moving some of these other things around, see how it can have up to 3 bumps. Because its degree is 4, then the maximum number of turning points, bumpy parts, it can have is 3. Now, it's still quartic. It doesn't have to have 3 bumps or 3 turning points, but it has at max 3. These graphs of rationals sometimes get lumped in with polynomials. By definition, I technically have to put them in a separate spot than polynomials because y equals 1 over x is the same thing as y equals x to the negative 1. The definition of a polynomial is that the powers on the variable need to be 0, 1, 2, 3, 4, 5, blah, blah, blah. But so I can't have the negative numbers on there. I also can't have square roots over a variable, or which is the same thing as a fractional exponent, something like that. I can't do that with the rational exponents. So this is a rational function, and it's technically not a polynomial, but you're going to see it a lot of times in that library of functions. So it has this kind of behavior right here. We have a vertical asymptote, we have a horizontal asymptote, and then when I look at y equals 1 over x squared, which is the same thing as y equals x to the negative 2, then I can't have any negative stuff because the negatives get squared out. So both sides go up. You still have that vertical asymptote. You still have horizontal asymptotes. Exponential and logarithmic graphs kind of go together, so let me elaborate on that. Here are 3 examples of exponential functions. You see how their parent functions all go through 0, 1. They all have this horizontal asymptote. They shoot upward. We can do some stuff to mess with that when they're no longer parent functions, but these are the ones we start with. So notice how when we increase this base number from 2, we get an e, it's a little steeper. When we get a 3, it's a little steeper than that. Notice that e is a number between 2 and 3. These are going to be very common functions for you to see. Also, the reason that these are going to be lumped in with logarithmic functions is because they are inverses of each other. If you reflect over y equals x, then you get, I put these both in red, you see how it does that flippy thing over the y equals x? So that means that y equals 2 to the x, its inverse function is y is equal to log base 2 of x, the common log. So right here where I have that coordinate 0, 1, on the logarithm I have 1, 0. Right here in the exponential graph where I have a horizontal asymptote, in the logarithmic graph I have a vertical asymptote. Does that nice little flip thing. Similarly, and here's going to be the big one, e, its inverse function would be the ln of x. So e, that number that we see over and over again that just keeps on popping up in natural things, its inverse is the natural log, or log natural. So these are inverses of each other. These are also inverses of each other. Those are all of them together. All of these are exponential. All of these are logarithmic. We're going to look at these kind of in pairs. Some of your trig stuff. These are your parent functions. Again, we haven't done any phase shifts or compression or stretching or any of that kind of stuff, but these are just the basic ones. So first of all, you have your sine and your cosine. I want to compare those for a second. They both have the same shape. They are pi over 2 apart from each other. The sine goes through the origin. The cosine has this nice little crest right here over the y-axis. You might refer to a sinusoidal shape, and we just mean this wave thing. And let me turn these off for a second. Tangent is the sine over the cosine. You get this behavior. But because it's the sine over the cosine, I'm going to put the cosine back on there. Notice wherever the cosine is 0, like right here, then you get a vertical asymptote on the tangent because the tangent's denominator is cosine. So whenever the cosine is 0, the denominator is 0, then you get a vertical asymptote. So that's something that we've done with polynomials, but now we're just doing it with trig. It should be a refresher also from a trig course. Not every place where the cosine is 0, then your tangent function has a vertical asymptote. You have this repeated pattern. And notice how to get through, let's say, an entire cycle of sine, you have to go all the way over to, well, you can't quite see my pi over 2. There. From 0 to pi over 2, you have to go this far over to get a complete cycle. But with tangents, it's only half of that, because it repeats faster. We do quadrant 4 and 1, and, well, then you get an asymptote and you start over. That makes sense on the unit circle. All right, here's your cosecant, but I want you to compare this one to its reciprocal, which is sine. So there's your sine graph. Notice how wherever there's a crest or a trough, then these two will meet. The range of sine is -1 to 1, which means that you can identify these. That's 1, there's -1, there's a -1, there's a 1. So if you were trying to draw the cosecant, what I would do first is I would sketch out where the sine is. Wherever the sine is a 0, then you're going to have a vertical asymptote, like right here, right here, right here, right here. Those are going to be where your vertical asymptotes are. This trough is going to match the other one's crest. And then you can, after you have your asymptotes in place, and then you have where your vertices go, then you can fill in the rest. So sine and cosecant are reciprocals of each other. Similarly, if I wanted to draw a secant, then I would probably sketch a cosine first. Let me make it dotted so that it's a sketch. Get it? Anyway, so I would probably figure out where the cosine goes. So right here at this crest, then you're going to get this vertex right there. You know, they're going to match up like that right here. And then also wherever your cosine is 0, you're going to get a vertical asymptote. And that's going to be separating these chunks of secant. So once you have identified where your cosine is 0, put vertical asymptotes there, and there, and there, and there. And then you can get your little pieces in there around your vertical asymptotes. Then you can graph your secant. And finally, the cotangent right here, it looks very similar to tangent. I'm going to put that one up for a second. See how they are going different directions? But your cotangent is cosine over sine, which means that wherever the sine is a 0, that's where you're going to get your vertical asymptotes here. Because right here, do you see where sine is a 0? You're going to get a vertical asymptote on your cotangent. Wherever your sine is 0, you're going to get a vertical asymptote on your cotangent. So notice how in this spot right here, this spot right here, this spot right here, this spot right here, those are going to be your vertical asymptotes for your cotangent functions. And one last little tidbit. Here is a sine wave. And when I want to look at sine of 2x, notice that it squishes it in and horizontally compresses that. So this is what your y is equal to the sine of 2x would look like. There's the original sine. Squishes it in like that.